phase changes. That is what we talked about, the attractive force between a solid, liquid, and gases. We said the solid, the attractive force is stronger than when they are in liquid phase and when they are in the solid phase. Now we want to examine how this phases changes. So when you heat a substance, the energy goes and breaks the intermolecular forces holding them in the solid phase, and it changes to the liquid phase. You continue heating, the liquid will change to the gaseous phase. The reverse is true. You increase pressure or cool it down, it changes to the liquid. As you continue cooling or increasing pressure, it goes back to the solid. Now we are going to look at some terms that are related to these changes. Vaporization. Vaporization is a term which is used when a liquid changes to the gaseous form. So this occurs when liquids absorb energy. If the acquired energy is greater than the intermolecular forces in the liquid molecules break away and escape as gas, as vapor. You can see it here, you see. This is a liquid, the molecules are held together. As you heat it, some of them at the surface break away from the liquid and they escape from the liquid phase. And if it is not covered, they will just leave. And eventually, you come and look at it, there's no water. All has changed from the liquid to the vapor phase and escape. Let's look at another term. Condensation. In condensation, gas is converted to liquid. So some molecules of the vapor will lose energy through molecular collisions. The result will be that some of the molecules will get captured back into the liquid state. And we call this process condensation. So, liquid to gas, vaporization. Gas to liquid, condensation. So, let's ask some questions. Why do our bodies feel cooler as soon as we step out of the swimming pool? Think of it based on conversion of a liquid to a gas, how it absorbs energy. So in this case, when you step out of the swimming pool, what actually happens? You have liquid on your body, then suddenly it is dried, but you feel cold. So think of it based on the conversion of liquid to the gaseous phase. So try and think of it and answer it on your own. So we want to talk about heat of vaporization. Is the amount of heat required to vaporize 1 mole of liquid. So that is heat of vaporization. The amount of heat required to vaporize 1 mole of liquid. Take note, it's 1 mole of liquid. It's sometimes called enthalpy of vaporization. This is how we represent it. This energy is endothermic. That is, it is plus, because you add it. We'll look at some heat of vaporizations of some substances. You see water? That is heat of vaporization. I want you to take note. You can use it as conversion factor, because it's energy per mole. Heat of vaporizations can be used as conversion factors. So let's see how we can use the heat of vaporization as conversion factor. Calculate the mass of water that can be vaporized with 157 kilojoules of heat at 100 degrees Celsius. The heat of vaporization is 40.7 kilojoules per mole. Molar mass of water is 18.0 grams per mole. So what do we have? We have the heat. This is what is given. We have the heat 155 kilojoules. That's the heat given. And we are searching for mass of water that is vaporized with this amount of energy. So we have to move from heat to moles to mass. In this case, we have to use conversion factor. So what is the conversion factor here? It's our heat of vaporization. Because we want to convert heat to moles, so we are going to write this conversion factor, which is 40. No, we want the moles. So we want the moles. So we are going to put 1 mole all over 40.7 kilojoules. Because we are going to start 155 kilojoules. So this is the conversion factor. We want to convert moles to mass. We are going to use our molar mass. So 18.02 grams over 1 mole. So this is equals to, cancel the kilojoules. I want you to take note. If you have difference in unit, make sure you bring them all in the same unit. But in this case, it's kilojoules. That's why I leave it like that. The moles cancel moles. Then you multiply everything above divided by everything below. Let's see what we are going to get. And make sure you check the significant figures. So let's get to that. So we want 155 times 18.02 grams divided by 40.7. So you see, what the calculator gave me is a long number, 68.6265, a long number. But we want 3 significant figures. So our answer will end here. So what do? You look at this number. This is less than 5. So we are going to cancel everything. So your answer should be 68.6 grams of H2. That should be your answer. We did not use this number because this is an exact number. Exact number does not affect the significant figure of your answer. This is exact number. This is also exact number. They have infinite significant figure, so they cannot affect the significant figure of our answer. That is why our answer is 68.6 grams of water. So that's what you're going to say. So that's what is given, and this is what we need. We have to move from joules to moles to grams. Here we are going to see what we are going to use to get our conversion factors. Then we are going to put the conversion factors down. So that's the conversion factor from the heat of vaporization, and this is from the molar mass. Now we set it up and solve our problem. So you see our answer is 68.6 grams of water. So please, this is set, I'll say this as extra credit on Canvas. So you see it as extra credit. Make sure you solve it to get the points. Now I want to talk about dynamic equilibrium. When two opposite processes reach the same rate so that there is no gain or loss of material, we call it dynamic equilibrium. Dynamic equilibrium is possible in processes that involve vaporization and condensation. So you see, we have this bottle, you have just liquid. But the liquid so bottle A, you see in bottle A, you have just the liquid. It is closed. If it's open, you will not have this equilibrium. But this is closed. So you see, water is turning into the vapor phase. So the particles that turn into vapor phase cannot escape. So some of them start losing their kinetic energy and going back into the liquid. Here, equal number of particles that go to the liquid is equal number changes back to the vapor phase. So you have that equilibrium. The rate of evaporation is equal to the rate of condensation. So you have this vapor in equilibrium with its liquid. And what do we call this vapor which is in equilibrium with a liquid? We call it the vapor pressure. We call it the vapor pressure of the liquid. Vapor pressure is the pressure exerted by the vapor when it is in equilibrium with its liquid. The weaker the attractive force between the molecules, the more molecules will be in the vapor. Therefore, weaker attractive forces, the higher the vapor pressure. So the weaker the attractive force, the higher the vapor pressure. So let's try to relate vapor pressure and temperature. Vapor pressure and temperature. Increasing the temperature increases the number of molecules able to escape the liquid. The net result is that as temperature increases, the vapor pressure increases. Small changes in temperature can make big changes in vapor pressure. So small changes in temperature, can make big changes in the vapor pressure. Let's examine it. Let's look at the vapor pressure curve. This is the vapor pressure curve. You see, this is vapor pressure and this is temperature. As temperature is increasing, you notice the vapor pressure is increasing. Place here, this is 760 millimeters mercury or Thor. So this is 1 atmosphere. This line here is 1 atmosphere. So you see, molecules like diethyl ether at 34.6 degrees Celsius, their vapor pressure has already matched the atmospheric pressure. because they're held by weak intermolecular forces of attraction. Ethyl alcohol, we call it ethanol, at 78.3 degrees Celsius, their vapor pressure has already matched the atmospheric pressure. Water, it matches it at 100 degrees Celsius. Ethylene glycol, you see, its intermolecular force is so strong that in this graph, we don't even know the temperature at which its vapor pressure match the atmospheric pressure. This affects the boiling point. Molecules that are volatile and their vapor pressure matches the atmospheric pressure boil at very low temperature because their vapor pressure matches the atmospheric pressure. And the boiling point of a liquid is when the vapor pressure is equal to the external pressure. That's when we have the boiling point. So vapor pressure curves. So you can see ethylene glycol. This is, what is it? Ethyl ether. It has the lowest boiling point because its vapor pressure matches the atmospheric pressure. And this boiling point where the vapor pressure matches the atmospheric pressure, which is 760 millimeters mercury, we call it the normal boiling point of the liquid. We call it the normal boiling point of the liquid. You see, the normal boiling point of water is 100 degrees Celsius because that is when its vapor pressure of the liquid matches the external pressure, 1 atmosphere. Let's try and answer this question. Which of the following is the most volatile? The one that the vapor pressure matches the atmospheric pressure at a lower temperature. So in this case, see this. So this is it. So the answer should be C. Let's have another question. Which of the following has the strongest intermolecular forces of attraction? The one with the highest boiling point. And in this case, I'm sure it's this. You see, it has the highest boiling point. This is it. So our answer should be B. So that is how vapor pressure and temperature relate. Now we want to talk about boiling point. The boiling point. When the temperature of a liquid reaches a point where its vapor pressure is the same as the external pressure, that is the boiling point. The liquid will boil. The liquid will start boiling. A normal boiling point is the temperature at which the vapor pressure of the liquid is equal to 1 atmosphere. Is equal to 760 millimeters mercury. Then we are talking about normal boiling point. But a liquid can boil when the vapor pressure matches the external pressure. So if you have a lower external pressure, the liquid will boil at a lower temperature. So that takes us to a question. Where will water boil faster? Top of the mountain or foot of the mountain? What you want to see is the area where you have a lower external pressure. And in this case, is at the top of the mountain, because at the top of the mountain, the external pressure is lower. So the boiling point of the liquid will be lower. So that is it. Let's try another example. Which of the following has the highest normal boiling point? So when we talk about normal, we're talking about 760 pressure. So we look at this. So it is this. So that is it. We can ask another question. What is the boiling point of ethanol when the external pressure is 500? So let's go to ethanol. Which is ethanol? This is ethanol. Then we are going to come down. We can say it's about 68 degrees Celsius. So we get to this point, then we come down to temperature, we can be able to match that. So we have seen the relationship between temperature and vapor pressure. Now we want to look at the heating curve of a liquid. The heating curve of a liquid. As you heat a liquid, its temperature increases linearly until it reaches the boiling point. To calculate the amount of energy that has been added, we have to use Q equals to mass times specific capacity of the liquid times change in temperature. We are going to call this Q1. Times delta T. Once the temperature reaches the boiling point, all the added heat goes into boiling the liquid. And the temperature stays constant, but you are adding heat. So for example, this part. So how do we get this energy from here to here? We'll call it Q2. Equals to delta H, vaporization, times N. So because it's constant, there's no change in temperature, we cannot put delta T. Then once all the liquid has been turned into a gas, the temperature can again start rising. So this is the next part, from here to here. We'll call it Q3. It's N times C times delta T. This T is T. This is T. So the total energy, Q total, is Q1 plus Q2 plus Q3. So that is our total energy. If we have to find the amount of heat that was added from here till here. We want to talk about Clausius-Clapeyron equation. Clausius-Clapeyron equation is a mathematical relationship between the vapor pressure and the temperature. So this is the linearized form of this equation. What do I mean? So ln P is equals to y, then minus delta H vaporization is equals to m, that's the slope. Then 1 over T is equals to x. Then ln P is equals to B. So this is a linear equation. And from a plot of ln P versus 1 over T, we can find the heat of vaporization. R is a constant. R equals to 8.314 joules moles per Kelvin. That's a constant. It must be given to you. So the slope, which is m, is equals to minus delta H vaporization over R. This is m. So a plot of ln P versus 1 over T will give us a straight line. And from the slope, we can find the heat of vaporization of the liquid. So let's take an example. Determine the heat of vaporization of dichloromethane given the vapor pressure versus the temperature. So this is our vapor pressure. But we cannot draw this temperature versus vapor pressure because we are not going to have a linear graph. So we need to draw a straight line graph. And from our equation, which is ln P equals to minus delta H vaporization over R times 1 over T plus ln beta. We have to plot the ln P versus 1 over T. So I'm going to show you how to do the plot. So we are going to go into Excel to plot the graph. Then we are going to come back and calculate the heat of vaporization. So let's go to Excel. So let's see how we can plot the graph in order to find our heat of vaporization. So